Hi, Professor Dyer here, talking about research in human development and family science. Right now, I want to discuss how scientists present the results of prevalence studies when the variable they're describing is numerical rather than categorical. We've already talked about the presentation of categorical data, but let's talk about numerical data. When the outcome is numerical, there are 2 points of data that get presented in order to describe what that data are like. The first is a measure of central tendency, otherwise kind of colloquially known as the average. What is the average score? You might think about this in a way that would be familiar to a lot of college students, is having taken a test in a class, and then the day after the test, the teacher says, you all say, how did we do on the test? And the teacher presents just one number as the central tendency, the average. They say, well, the average was a 75%. And they might think that's pretty good, right? What they're presenting typically is a statistical mean. There are other averages, and some situations call for other averages to be used other than the mean. But for this class, just for simplicity's sake, we're going to talk only about the mean as a measure of central tendency. The second thing that the scientists will always present when they're sharing prevalence data on numerical variables is how much variability there is in the data. And this can be presented with a relatively less sophisticated indicator of the range, which is just to say, the highest score was 95 and the lowest score was 20. That just tells us the range. They go from this to that. And a much more sophisticated measure of variability, which is standard deviation. So let's talk about these a little bit more one at a time. The average, as I've said, is a measure of central tendency, and the most common one is the statistical mean. You know how to do this. You've been doing it since about 3rd grade, I think. You add up all the values and then divide by the number of values that were there. My example here, if the teacher says the average score was 75, you might imagine that everyone in the class got a 75, and then that would be the average. But that's not always the case. I mean, that's rarely the case, actually. Typically, there's more variability. So here's a case where there's not much variability. Maybe the lowest score was a 70, someone got a 75, and someone got an 80. So everybody did within that 10-point range, but that average is still going to be 75. But sometimes the variation is much more extreme. Consider a case where 2 people in the class scored 100% and one person scored only 25%. That is also going to have an average score of 75. So you see that just the average score doesn't tell us quite enough about the data. The mean, the average of a distribution, is not a useful piece of information unless we know about the distribution, meaning the variability of scores and how they clustered. Statisticians like to use this analogy that a man with his head in the freezer and his feet in the oven is on average a very comfortable temperature, but that doesn't accurately describe what the situation is. We sort of have to know where the extremes are and how much variability there is. So we do that a couple of ways. One way is to present the range. That just tells us how much distance there is between the highest and the lowest score. Standard deviation is a more standardized way of doing this, but let's think of all of the test scores if we plotted them. Maybe 75 is that middle line down the red middle part of the distribution. What we're saying, if it's a normal distribution, and not everything is, but for the sake of this conversation, we're going to pretend that most of the numerical things we care about are normally distributed. Let's say that down the middle line there, the middle of the red, is 75%. And then some people got higher than 75%, and some people scored lower than 75%. But a normal distribution means most people scored around the mean, and they're kind of distributed in this way, where where they tail off in one direction and they tail off in the other direction. That's what's meant by a normal distribution. Well, what a standard deviation does is it standardizes based on the percentage of scores in each at each part of the distribution. So test scores, we're going from say 0 to 100, but maybe you're looking at some other scale. How many times last week did you have dinner with your family, and that might range from 0 to 7 instead of 0 to 100. So different things we measure are measured on different scales, and so standardization removes the whole scale from the process. It just says, how can we consider the data in a standardized way? And so the way it works is one standard deviation plus and minus should encompass then 68% of the scores. So if I tell you what the average score is, let's say on the test it's 75, and I say, and there's a standard deviation of 5 points, then you know that 68% of the population scored between 70%, because that's 75 minus 5, and 80% because that's 75 plus 5. And you know that 68% of the population falls within those two scores. That's how a standard deviation works. If I went out 2 standard deviations, I would be encompassing about 95% of the sample would fit within 2 standard deviations. So I hope you can see that a small standard deviation means most of the scores are clustered right there around the mean. And a large standard deviation means they're spread all over the range. Let me show you some examples. I'll start with one you've probably seen before in a child development class. You probably studied IQ and how IQ works. IQ is normally distributed. The tests are constructed and scored such that a mean score and an average score is 100. That is the average IQ score. The standard deviations go out plus and minus. One standard deviation would get you from a score of 85 to a score of 115. And that is 65% of the population has an IQ between 85 and 115. And then 95% of the population has a score within 2 standard deviations. So from 68 to 132. I hope that is one you've seen before. And so you can start to connect the concept of a standard deviation to this graph that you've probably seen before with those lines. Those are indicating standard deviations. Another place you've probably seen standard deviations before, even though it's not explicitly labeled as such, would be a graph like this that you probably saw on, it's often on the inside cover of a child development textbook. Developmental milestones and what is the average age at which kids meet these milestones. So for each one of those green bars, you see the black line in the middle of it. That is the mean. That is the average age at which children in a normal healthy population meet that developmental milestone. So like, let's look at sits without support. It's right there kind of in the middle. Sits without support, it looks like the average age is about 6 months. That's when kids can sit without support on average. But the green bar around it presents 2 standard deviations. So what they're saying is 95% of kids sit without support somewhere between 4 months and 8 months. They're telling you how much variability is normal here. That's useful if your friend has a 7-month-old baby and says, when do kids start sitting without support? And you look at your chart and you say, well, the average is 6 months. And she says, well, mine is 7 and she's not sitting without support yet. You can say, well, most kids will reach this milestone by the time they're 8 months. So I would wait until 8 months. And if she's still not sitting at 8 months, then you might want to start investigating what the problem is. But there doesn't seem to be any problem right now. She's still within this range of normal because these are normal, healthy kids, and 95% of them sit without support in that time frame. So that's a really important use of standard deviations and kind of knowing what they mean and how to read them. please notice the line right under it. When should my baby roll over? The average age is also 6 months, but notice that on that one, the standard deviation is quite a lot larger, because there to include 95% of the population, they might roll over as young as 2 months, and they might roll over as late as 9 months. So that one has a lot more variability, as a standard deviation is quite a lot larger. Another example from some research from Zurich. This is a longitudinal study measuring how much sleep, how many hours of sleep children get in a 24-hour period. And on the left-hand side, you can see we're talking about 1-month-old babies. They sleep on average. Go to the middle of the blue bar, and you'll see they sleep on average 14 hours and something. 14 hours and a half, or 14 hours and 15 minutes, something like that. That's the average. But the dark blue around that middle line, that reflects one standard deviation, plus and minus one standard deviation. So we know that there's kind of a lot of variability in terms of how much sleep a 1-month-old baby gets. And the middle blue bars on either side of the dark bars, that's 2 standard deviations out. And then the light blue bars on the outside, those are 3 standard deviations out, which gets us to 99% of the population. So it appears that in infancy, in the first year, there's a ton of variation from baby to baby. A 1-month-old might sleep on average 14 hours, but they might sleep anywhere from 9 hours to 19 hours in a day. And so that describes 99% of 1-month-old babies are sleeping anywhere from 9 months to 19 months. That is a ton of variation. The standard deviation is huge. If you track them as they get older, if you look at the far right side of the screen, those are 16-year-old children, and you can see the standard deviations have shrunk considerably, and now there's not much variation at all. They're sleeping between 7 hours and it looks like 9.5 hours. So that's still some variation, but it's nowhere near the kind of variation that existed for the newborns. Those lines around the averages are depicting the standard deviations. One more example I'll share with you. This is a study of anxiety and depression in college students. And the red line on the graph depicts how much anxiety and depression there is in the course of a semester prior to COVID. And you can see that anxiety and depression start low and gradually increase and increase and increase until about week 7. And then it holds stable and slightly declining as we get closer to finals. But then when we hit finals, anxiety and depression really drops off kind of the charts. But look at the gray bar around that red line. It's pretty narrow, meaning there's not a lot of variability from student to student and how much anxiety and depression there are. All of them are having a similar experience where their anxiety and depression is low at the beginning of the semester. It increases and increases and increases as they go through the semester, and then it drops off after finals. And most college students are sharing a very similar experience. But if you look at the blue line, that is during a COVID-19 term, one of the terms. Then we were forced into remote instruction, and there was a lot of sickness and fear around us. And you can see that the blue line is in many places higher than it was in the red line, and especially right there around finals, you can see it's a lot higher on average. But I think the more interesting part of the story is to look at the gray band around the blue line, and that is representing well, this doesn't tell me if that's 1 or 2 standard deviations. I'm guessing it's 1 standard deviation out, but you can see that it's way broader. It's much broader than the gray band around the red line. So the standard deviation during COVID was a lot higher than the standard deviation around anxiety and depression prior to COVID. And what that's telling us is that people experienced COVID differently. For some people, they didn't have much anxiety and depression at all. It really almost reduced their anxiety and depression. Maybe they didn't have their commute that they used to have. Maybe they didn't have to worry about gas money, which had been a big concern for them prior to COVID. Maybe they didn't have to worry about childcare because they were able to attend school while they stayed at home. And so maybe their anxiety and depression actually lessened, but for other people, their anxiety and depression jacked up. And so now there's just so much more variation. You've heard the saying, we might all be in the same storm, but we're not in the same boat. This is what this is suggesting. There's a lot of variability around anxiety and depression during that year after COVID came to the world than there was beforehand. And so the story is in the standard deviations in that case. To wrap this up, well, presenting numerical data is more complicated and frankly less intuitive than presenting the categorical data. So this is a little bit harder. Anytime numerical data are being presented, the scientist is going to include two things: central tendency, which is often depicted through the mean, through a statistical mean, and the degree of variation in the scores. And this is typically presented with a range and a standard deviation. When the standard deviation is small, it means there's not much variation. When it's larger, there's more variation. And then maybe just keep in mind this rule of thumb that plus and minus one standard deviation is going to equal about 68% of observed scores. 68% of the sample, that is going to fit within that range there. And then plus or minus two standard deviations is going to encompass 95% of the population. All right, well, I hope this helps as you understand the presentation of prevalence data regarding numerical variables.